All right, good morning, everybody. Couple logistical things. We do have a test coming up on Friday. I will see to putting together some practice problems, possibly distributing a previous test I gave in a previous semester from this point. So you've got some idea of what to expect. The test will essentially cover what we've done so far. So thinking carefully about arrays, singly linked lists, stacks, and queues, which we're going to talk about today. The emphasis on the test will be more on conceptual understanding than necessarily code as such. So there will certainly be a couple of questions where you might write some short segments of code, and there will definitely be questions where you read bits of code and do some analysis of them. But you should also be ready for some questions where I ask you to sketch out a linked list or a data structure or something like that, or reason in some more abstract way about something. But really, anything we've talked about through today will be eligible material for the test. So, so there's that. There's that. So, what about today? So, we've talked quite a bit now about the idea of a stack. And what characterizes a stack is that it's got these operations, that you push something in, you can pop something out, and there's some way to see what you would get if you popped something out. Related to this, it's important to know whether a stack is empty. And a stack has a special ordering, last in, first out, LIFO, as it's often abbreviated. And something that I hope you've come to appreciate over the last couple of weeks is that the LIFO idea turns out to be really, really useful for a lot of things. Specifically, we've discussed the application to postfix arithmetic. We have discussed the idea of the call stack, and we've discussed search with backtracking. And so these applications are examples of where the idea of last in, first out has proven pervasively useful in computer science. So essentially, any computer scientist knows that a stack does these things, it's LIFO, and it lets you do these things. Something that's interesting about the postfix arithmetic in particular is that it's pretty frequent for a compiler to translate a parenthesized expression into a postfix expression and then evaluate it using a stack. So these two ideas actually wind up being closely tied together. They interact strongly with each other because it's just a lot easier to generate code that does postfix arithmetic than everything involved with parentheses and order of operations. And so it turns out an easy way to do that is just translate it, which reflects an underlying idea that also pervades computer science, which is the following. Whoops, just a second. When in doubt, add another layer of abstraction. When in doubt, just add another layer of abstraction. So what do I mean by this? Basically, a lot of the problems we ask computers to solve are just really complicated, and it's not terribly easy to think about how to solve them. And so the mindset that computer scientists take is when you're stuck with some annoying problem, figure out, how do I just simplify it even a little bit? And by simplifying it even a little bit, can I make my life easier? Can I make this more tractable in some way? And that's a lot of what we do. And that's a lot of how we mentally organize our thoughts when we're trying to solve problems. And so the idea of parentheses are annoying to process, postfix arithmetic is easy to process, is one of many examples of this practice. So that's a little review of stacks. Any questions about stacks? So what we're going to look at today is take that last in, first out idea and just tweak it a little bit. Instead of last in, first out, what do things look like if we go first in, first out? Or FIFO. So we're going to think about this in a couple of different ways. We're going to first think about it in terms of how do you implement this using both arrays and linked lists. And then, time permitting, we'll think about how does this change things? What new ideas are made available by the idea of having a first in, first out data structure? Much as stacks enable us to do a lot of things, first in, first out will enable some different things. So as a data structure, you can envision both last in, first out and first in, first out as representing essentially the same kinds of operations, but perhaps with less loaded vocabulary. So what I mean is any sort of data structure like this has a notion of add something, remove something, check if it's empty, and peek at the next thing to be removed. So the vocabulary that I am extracting is the idea of push and pop. So push and pop, when you talk about those, you must be discussing a stack. Add and remove are kind of more generic terms that are not freighted with any particular baggage. So when thinking about adding and removing with first in, first out, traditional terms would be NQ and DQ. It takes a lot of U's and E's to get to DQ something. So there's NQing and DQing. And so this data structure, first in, first out, is known as a queue. Any guesses as to why this data structure is known as a queue? A stack is like the trays in the cafeteria, right? The last tray on top is the first tray off. What do you all think is the real world metaphor of a queue? Yeah, Jake. Waiting in line. That is correct. And to add to the humor value of this, I first learned the term queue strictly in reference to this data structure. It was only at some point traveling in Europe that I learned that in British English, getting in line is getting in a queue. And I felt naive. Anyway, yeah, it's getting in line. Whoever's first in line gets to be the first one served. Actually, now that I think about it, we can extend the cafeteria idea, right? So the trays are in a stack, but getting food, that's a queue. Getting something on your tray requires going through a queue. So queues can be eliminated. implemented efficiently using both arrays and linked lists. And so we're going to explore first how we might implement a queue efficiently using an array. For now, let's imagine, and we'll relax this restriction in a few moments. For now, let's imagine a bounded queue that is n items max. Any guesses as to why I'm suggesting let's think about a bounded queue with array implementation? How does this simplify an array implementation, you figure?
An array can only have a predetermined length.
That's right. An array as such only has a predetermined length. How did we deal with that with stacks?
When it filled up, we made a new array and transferred everything.
Exactly. When it filled up, we made a new array and we transferred everything. Ultimately, we'll do the same thing with a queue. But for now, just to get the concept across, we're going to imagine a bounded queue with an array of size n. Okay. So I've got an array, and let's imagine n is 8. Why 8? Because it's easy to draw. Nothing deeper than that. Okay. So if I've got a capacity of 8 items. Now, if I'm going to implement my queue in an array, some key ideas are when I add something, I need to know where it's going to go. And when I remove something, I need to know where it's coming from. Where it's coming from. So let's just think about adding. When I add something to my queue, where do you think I might put it? At the beginning. Why not, right? So let's imagine I add the number 5. So 5 is at the beginning. Now I'm going to add the number 4. Where should it go? After 5, sure. Now I'm going to add 12. Where should 12 go? After 4. And now I'll add 13 for good luck. Where will that go? After 12. Now I am ready to dequeue. I'm ready to remove something from my queue. What do I remove? I remove 5. So I better switch to my eraser. And so I'll put things I've removed over here. So I've removed 5. So now I'm going to add to my queue. I'm going to add 7. Where does 7 go? After 13. Well, if it did, what happens to 13? So what you're suggesting is maybe we could just scoot everything back over. And you know, we can do that. We could put 4 here. And then we could put 12 there. And then we can put 13 here. And then we can put 7 here. And you know, 7 was never there to begin with. Okay. So this can work. So now if I dequeue 4, what I can do is scoot everybody over, right? So I could have 12 go there. I could have 13 go there. And I could have 7 go there. And then if I add 9, that could go there, say. And this would be a correct implementation of a queue. This will work. But I have a question for you all. Does this scheme have any disadvantages? It is correct, and that is not to be underestimated. But is there anything about it that makes you kind of go, I'm not so sure about this in terms of efficiency?
I mean, every time you, depending on how long your array is, every time you add or remove something, you have to move that many items down.
So you are mostly correct. Every time you remove something, you have to shift everything down. Adding is cheap, though, right? Adding is just as cheap as it was with the stack, but removing, that got expensive. So I'm going to present a challenge. Can we reframe how we think about this so that we can make removing just as cheap as adding while preserving a cheap addition? So we're going to do a couple more of these to maybe see what we can do with our imagination in this regard. I'm going to add a 14. And then I'm going to add a 3. And now I am going to remove 12. And I'm not going to shift because that's the expensive part, as Caleb correctly pointed out. And now I'm going to add a 2. And now I'm going to add an 11. And now I'm going to pose the following question. Is the queue full? Where could I put my next entry, which happens to be 16? I can. Now I am ready to DQ. Where will I DQ from? So if I DQ from array 0, I get 16 out. That doesn't sound good. Okay, I can DQ from array 1. That's true. So I can remove a 13. Now I DQ again. Where will I DQ from? Where, Ivy? From 2. Whoops, I'm erasing. Yeah, I can DQ from 2. And now I'm going to insert -1. Where will that go? At 1? Why 1, Elijah? I could put it at 2. Why would I put it at 1?
Because the order we're kind of shifting down and eventually set zero.
You're right. The order we're kind of shifting down and we want to reset to 0. Whoops, that really didn't work. There we go. That's better. That's better. So this is kind of a neat scheme, right? The underlying implementation strategy is what we can call a circular array. A circular array where we pretend that the array doesn't have an ending. It only has a new beginning. Okay, that was way too philosophical and foofy. But in any event, we have this circular array. It can wrap around. Now, what auxiliary data items do we need to keep track of the circular array? Bear in mind, with the stack, we had one such item, right? What was that one auxiliary item we used in the stack? And what was the significance of that index, Elijah?
It just let us know where we were.
Well, let us know where we were. To what end? Where we were It actually did track that. It kept track of how many total items there were. And that in turn enabled us to figure out both where to push and where to pop. So we had where to push, where to pop, and the size. 3 distinct ideas, 1 convenient variable. What I'm suggesting here in the case of the circular array implementation of the queue is that 1 bit of extra information is not sufficient to express those 3 ideas. I'm going to write down the 3 ideas so you can think about this, right? For a circular array, we need to keep track of, where does data enter the array? Where does data exit the array? And how many items of data are in the array? So we have 3 related but distinct concepts. And we had the same 3 concepts with a stack. The same 3 concepts with the stack. But we were able to represent them using just 1 variable. I'm suggesting with a queue, 1 variable won't quite do it. And so here's a little challenge. How can we represent these 3 ideas? What types of variables do we need? How might we describe them? So, 3 ideas. How do we represent them? Yeah, let's walk through our example again. So what I'm going to do actually is I'm going to erase everything. I'm going to make it all disappear, including these guys. And here's what we'll do is we're going to track each of these ideas as we go. All right. So right now, at the beginning of time, what is my entry point? I can't hear you all. It's early. Oh, yeah, that was better. Okay. 0. Oh, okay, that was not better. Our entry point is 0. What's our exit point? Is there an exit point? I'm going to mark this as the empty set. Exiting is undefined. So we're just thinking of things at the conceptual level here, okay? And what's the size? 0, okay. So now I'm going to add an item. What is my entry point now? 1. What is my exit? 0. And what is my size? Okay, let's add a 7. What is my entry point now? 2. What's my exit? And what's my size? 2, yeah, definitely. Okay. So now we're going to do a DQ. So when I do a DQ, I remove 11. And now, what is my entry point? It's still 2. What is my exit point? It's still 1. Or, no, yeah. Wait a minute. The exit should have been 0 back here. Whoops. My exit is now 1. And what's my size? Okay. So, an important observation. These first 3 steps, the entry and the size moved in lockstep with each other, just as they would have in a stack. And so, just by examining them, it would have been tempting, since we hadn't done any DQs yet, to think, that's just the same thing. But they're not, right? The size and the entry point are distinct values, as is the exit. All right, let's do a few more of these. So we're going to add 9. What's our entry point now? What's my exit? Still 1. What's my size? 2. Now we're going to put in a 3. What's my entry point now? What's my exit? Still 1. And what's my size? Okay. Now, seeing these numbers up here, even the crossed out ones, let me pose this question. Do we need 3 distinct integer variables to track the entry, the exit, and the size? So I'm going to do some voting here. We might need 1 variable, we might need 2, and we might need 3. Who thinks we can get away with 1 variable to represent these 3 quantities? Good, you are correct. Who thinks we can do 2 variables to represent these 3 quantities? 1. Who thinks we need 3 variables to represent these quantities? 8. 8, but it's really 4 because you only had your hands halfway up. Okay. It's 8. Okay. Well, there was only 1 vote for 2, and that was Professor Simi working in the back, who may or may not have inside information. So, I'm going to throw out a little challenge. Can any of you, looking at how these values change over time, envision how maybe you could do this with just 2 variables? You can definitely do it with 3, but you can actually do it with 2. Yeah, Elijah.
Subtract the enter from the exit.
Subtract the exit from the enter. Yes. Isn't that interesting, right? You've got 1 minus 0 is 1, 2 minus 0 is 2, 2 minus 1 is 1, 3 minus 1 is 2, 4 minus 1 is 3. And that'll work. It's going to get a little tricky once we wrap around. But conceptually, the idea is pretty on target. In general, this proves to be a really powerful idea. I'm going to stop trailing them now because we're running out of space. But right now we have an enter of 4, an exit at 1, and size at 3, right? So I'm going to add several more. So 2, 4, 9, and 8. And so at this point, our entry point, what the? Okay. Obviously, I'm still getting used to the software here. All right. So let's erase. So our entry point is now 0. Our exit is now 1. And our size is now 7. Again, in principle, you can actually calculate based on the wraparound. But, and the reason that you can figure it out is that enter is now less than the exit. And so that lets you turn things around a little bit. When you implement these on your own, ultimately, if you need 3 variables to get it correct, by all means, use 3 variables. But just know it can be done in 2. So now I'm going to DQ. I'm going to DQ 7. And when I DQ 7, enter is still 1, but exit is now 2, and size is now 6. And now I'm going to NQ a 1. And when I do that, oops, enter is now 1, exit is 2, and size, whoops, is up to 7, as a matter of fact. And so note that these three items are sufficient for representing everything we need to know about the circular array. This is a really powerful idea because something we had discussed before was the fact that arrays weren't so hot for adding on both ends, right? But it turns out, actually you can if you do a little bit of extra bookkeeping on the side. If you do a little bit of extra bookkeeping, you can actually add to either end of an array, which is a pretty powerful idea. Now, let's imagine the resizing scenario. So we're going to add a 6. And now enter is 2, and exit is 2, and the size is 8. And now I want to add a 5, like there. And that's not going to work now, is it? So I need to resize. And we're going to use the same type of strategy that we used with the stack, right? So instead of an 8-element array, we are going to have a 16-element array. And typically, what we will do at this point is reset our entry to be back to 0 and just move everything over to the left. We don't need to maintain the circular structure exactly where it is when we move it down. And in fact, it's undesirable to do so, like to do an index-to-index relocation. That causes problems because the way this is arranged is a function of the size of the capacity of the array we previously had. So conceptually, the simplest thing to do is start with your exit point and then copy everything down. 4, 9, 8, 1, 6, and then you can add 5 here. And so enter is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Exit will, of course, be 0, and the size is 9. And then you can just keep going as you see fit. You know, this, by the way, is the reason that circular arrays are not the primary array abstraction that tends to be used in practice. So the stack type array is in fact what something like ArrayList is doing. You add to the end, you can remove from the end, it's cheap, but you don't want to add or remove on the front. A circular array, however, because the elements get their indices changed when it resizes, isn't as full-featured an array as we might be accustomed to. Because there's some extra complication of figuring out where did everybody go? And that's a lot of why we still tend to think of arrays as a one-ended changer as opposed to a change on both ends kind of a data structure. You can certainly implement efficient operations on the ends, both ends with an array, but then you give up the random access in effect because of what happens when you resize. So that's the array implementation of a queue. Any questions so far? One thing I hope you all are learning from this is when we talk about something like an array or a linked list, an array is not just an array. A linked list is not just a linked list. We can use them to create new abstractions that have them as the back end. And at the back end, it's still an array or a linked list or whatever, but we're building other ideas on top of them. So in that same theme, we're now going to think about the idea of the linked list. implementation of the queue. So first we'll review the linked list implementation of a stack. So for the linked list implementation of a stack, we have a notion of a pointer to the top of the stack. And then you've got a null at the bottom of the stack. And each node points at the one that's below it on the stack. And so now we need to think about this in terms of a queue. Analogously, as to what happened with the array implementation of the stack, switching to the linked list implementation of the queue requires adding some more auxiliary information. That is, with a stack, the entry and the exit points are the same. They both happen through top. If I want to add to my stack, push something onto the stack, I just allocate a new node, and then I tell top to look at that node instead. And if I wish to do a removal, why? I just take top, I have it point at the successor to itself, and then this value gets returned wherever. But with a queue, that's not really going to work because I have to add at one end and remove at the other end. Now, given the monotonic directionality of a linked list of this form, we know that we're going to need pointers on both ends. So we're going to need some kind of a pointer over here, and we're going to need some kind of a pointer down here. So here's a question for you all. Between these two pointers, which is going to be the entry point and which is going to be the exit point? Okay, so you're suggesting the top is the entry and the bottom is the exit. Let's try it out. Let's see how it works. So initially I have my nothing list. So I add my first item, which I'm going to declare to be get over here, 7. And both my entry and my exit are pointers to that node. Now I will add something else. I'm going to add a 5. I'm going to update my entry to point at 5, and then 5 is going to point at 7. Now I'm going to add a 4. I'm going to update my entry, to point at the 4. And now I think I'm ready to do some dequeuing. So I am going to dequeue my 7. And now, where is my exit pointer going to be pointing? How does it know? Does it know? Not really. It turns out when we exit, we want to know, based on the node exiting, who's next, right? So it turns out when we're exiting, we want to have a pointer backward to the next one to exit. So we're going to reverse this, and we're going to do the example again. So initially, we have 7. the entry is pointing at 7, and the exit is pointing at 7. So now we're going to add 5, and it is really easy to mix this up. 7 is the exit, and it points at the guy that'll exit after it. And our new entry is actually pointing at 5. Now we add 3. So 5's next is pointing to 3, and we tell entry to point at 5's next, like so. Now we're ready to DQ. We DQ 7, and now exit is seriously exit? Okay. Exit is now pointing at 5. Exit is now pointing at 5. And so that gets us our linked list implementation of the queue. It turns out for entry, the node that is the last thing added has a pointer to null. And when you add something else, you create the node, and then you can set its next pointer to the newly created node. But when you're exiting, you need to know who gets to exit next. And that's what the sequence winds up telling you. Cool. Any questions about this? Any questions? All right. So I guess this leads to the next question of, what's this good for? So let's review things that stacks were good for. And just see, are these relevant, or do we need to think about other things, right? Postfix arithmetic. So the idea of postfix arithmetic is you have something like 2, 3 plus 5 minus 7 times, right? And so you can envision 2 and 3 go on the stack, and then you add them, and you put a 5 on the stack. Then the other 5 goes on the stack. Wow, this example was terrible. You subtract them, and you get 0, and then 7 goes on the stack. You multiply them, and now you've got a 0 on the stack. Does it look like a queue could conceivably help with processing arithmetic? Does it give you anything a stack doesn't? Not really. Next, let's think about the call stack. So I have some function f that calls function g. G calls h. H finishes up, returns to g. G finishes up, returns to f. With a queue, you might imagine something like this. F calls G, which calls H. H finishes up, and we go all the way back to F. That doesn't look really helpful. Now, let's think about the backtracking search. So last time, we thought about how I'm considering a path, and then I've got 2 alternatives. And I follow out one alternative, and then I've got 2 alternatives. I follow out one, there's another. Then I get out here, and it's a dead end. So then I come back here, I follow that out, and maybe that's a dead end. So I come back here, follow that out. Yeah, maybe I've got an alternative, that's a dead end. I come back here, that's a dead end. And, I come back here and I finally get to the exit. Yay. Now, the stack is where we stored all of these alternative paths. We would push them on top of the stack. Then when we backtrack, we would jump back to them. So here's a question. Can you imagine a queue being useful in this context? What would a queue do that a stack wouldn't? Yeah, Elijah. Run through all your possible options. Please elaborate.
It would go, through one, and then it would come back, and then
So it gets to like here, it's got two choices.
and it would put both of them, I guess, and then go one way,
Mm-hmm.
and then you would go all the way through your queue, and it would come back to that next one that it was above, and then it would go do the next part, and it would just continue on to it.
Then it would jump back here, and so forth. Whether or not this is useful is not immediately obvious, but I hope that you do see that this is at least interesting, right? When we looked at the call stack, this approach had no relationship to the semantics of the domain. That is, the whole idea of function calling is last in, first out. You go first in, first out, you've got spaghetti. You've got a mess. I love spaghetti. That wasn't meant to be prejudicial. But it doesn't really work, right? Here, with the search problem, it's easy to see that it would work. It might not be immediately obvious what it gets you, what it buys you, what you can now do that you couldn't do with the stack. But it should be pretty clear that it at least would work, and it should also be clear that what it does is distinct. What it does is different in some way than the stack. The stack kind of charges forward helter-skelter until it runs out of ideas and then backtracks. This version is like maybe a little more thoughtful. Like, okay, let's go out here, and now let's make sure everybody gets a turn. And now we'll go here, and we'll make sure everybody gets a turn. So we're going to be thinking about this a lot this week. In your lab for this week, which we'll have tomorrow, we're going to continue working on the maze. Now, if your maze doesn't work perfectly, no problem. I will be providing, admittedly disguised, correct code for you to build upon. Okay? But what we're really going to look at is what's the difference between using a stack to explore the maze versus using a queue to explore the maze? What does it buy you to use one or the other? And a lot of why we can think about it this way is that coming all the way back up here, both stacks and queues can be envisioned as different implementations of this same abstraction. Add things, remove things, check if it's empty, and peek what's about to come out. That in turn lets us describe an interface for search. Just like that. So we're going to explore using our stack and our queue to see what's the impact on how we explore a maze. And as I mentioned last week, the idea of a maze is a really concrete example of something we can search, but these search strategies are something that are applicable in many realms and domains. You can take the strategy idea out of the maze embedding and use this as a way to solve a wide variety of problems. So We will think more about this tomorrow and even more about it on Wednesday. And then we'll have a test on Friday. See you then.